Hello, my dear students. Welcome to IK Sir Chemistry classes. Here we are in lecture number 12 on the chapter Symmetry and Group Theory. In this video, we will discuss symmetry and optical activity. Let us see, first of all, what is optically active compound. The compound which rotates the plane of plane polarized light either in the clockwise direction or in the anti-clockwise direction when passed through its solution or liquid state is called an optically active compound, and its property of rotating plane polarized light is called optical activity. Let us see it again. The compound which rotates the plane of plane polarized light either in the clockwise direction or in the anti-clockwise direction when passed through its solution or liquid state is called an optically active compound. And this property of compound of rotating the plane polarized light is called optical activity. Let us illustrate the optical activity of a compound with the help of diagram. It is plane polarized light. The plane polarized light consists of electromagnetic radiations of the same wavelength and vibrating in the same plane. This plane polarized light is passed through the solution of optically active compound. As a result, the plane of vibration of plane polarized light is rotated by an angle alpha, which is called optical rotation, and the compound whose solution or liquid state has been taken here is called an optically active compound, and this property of the compound to rotate the plane of plane polarized light is called optical activity. Condition for optical activity of a compound. Any compound is optically active only when its molecule is non-superimposable to its mirror image. Any compound is optically active, that is, rotates the plane of plane polarized light when passed through its solution only when its molecule is non-superimposable to its mirror image. Means the molecule cannot be superimposed on its mirror image, is optically active. Such molecule is called chiral molecule, and its property is called chirality. The word chirality means handedness, hand-like. The molecule which is non-superimposable to its mirror image is called chiral molecule, and its property is called chirality, which means handedness, hand-like. Diagrammatic representation of handedness. It is after our left hand. This is left hand of a man, and if we place a mirror here, its image will be formed here. Our two hands are mirror images of each other. Our left hand is just the mirror image of right hand. If this right hand is rotated by an angle 180-degree and two hands are placed one over another, they cannot be superimposed. it is our left hand, and it is our right hand which has been rotated by 180 degree. And if we try to superimpose our left hand on the right hand, it is not possible. It means our left hand is just mirror image of right hand, and this property is called handedness or chirality. Diagrammatic representation of chirality of a molecule. This molecule is bromochlorofluoromethane. It is bromochlorofluoroethane. If we place a mirror here, its image will be formed here. It is the mirror image of this molecule. The image of F is formed here, the image of Cl is formed here, and the image of bromine is formed here. If this mirror image is rotated by 180 degree, let us see. If this mirror image of this molecule is rotated by 180 degree, the F atom will come here. Cl atom, which is towards the viewer, goes to back side, that is away from viewer. Bromine atom, which is away from viewer, comes towards the viewer. This mirror image has been rotated by 180 degree. Now let us try to superimpose this molecule, this mirror image, on the original molecule. It will not be superimposed because here we have bromine, while at this position here is chlorine. Here we have chlorine at this position, and at equivalent position bromine is present. Therefore, this mirror image of this molecule is not superimposable. This molecule is not superimposable to its mirror image, and hence bromochlorofluoromethane molecule is chiral, non-superimposable to its mirror image, and it is optically active. Let us see another molecule, dichlorofluoromethane. If we place a mirror here, its image will be formed here. F, the image of this Cl will be formed here, and the image of this Cl will be formed here. And if this mirror image is rotated by 180 degree, fluorine atom will move to here. The Cl atom, which is present towards the viewer, goes away from viewer. This chlorine atom, which is away from viewer, comes towards the viewer. And let us now try to superimpose this mirror image on the original molecule. It is superimposable. The chlorine atom superimposes on this chlorine atom. This Cl atom is eclipsed on this position, Cl atom, and F is superimposed on this F atom. It means the molecule of dichlorofluoromethane is superimposable on its mirror image, and therefore this molecule is achiral, is superimposable to its mirror image, and it is optically inactive. Optically active molecule we have taken bromochlorofluoromethane. It lacks plane of symmetry, it has no center of symmetry, it has no axis of improper rotation, as well as it does not contain axis of proper rotation. This optically active molecule, bromochlorofluoromethane, lacks these elements of symmetry. On the other hand, dichlorofluoromethane molecule, which is optically inactive, lacks center of symmetry, axis of improper rotation, and axis of proper rotation. But this molecule has plane of symmetry. This plane passes through carbon atom, hydrogen atom and fluorine atom and bisects the angle Cl carbon Cl bond angle is bisected by this plane of symmetry. It means if a molecule has plane of symmetry, it is optically inactive. Now let us see dissymmetric molecule. Any molecule is non-superimposable to its mirror image. That is chiral. That is optically active only when it lacks the following elements of symmetry. If a molecule lacks the following elements of symmetry, it is non-superimposable to its mirror image. It is chiral and optically active, and these elements of symmetry which should not be present in dissymmetric molecule are plane of symmetry, center of symmetry and axis of improper rotation. The molecule lacking the above elements of symmetry is called dissymmetric molecule. If a molecule does not contain sigma I and Sn, it is called dissymmetric molecule, which means the molecule devoid of symmetry. The molecule deficient of symmetry, and such molecule, that is dissymmetric molecule, is non-superimposable to its mirror image, chiral and optically active. Let us see it again. The molecule which does not contain plane of symmetry, center of symmetry and axis of improper rotation is called dissymmetric molecule. It is chiral, non-superimposable to its mirror image and optically active. That dissymmetric molecule is optically active. It must be noted that the dissymmetric molecule is optically active. Now, there is another term, asymmetric molecule. If the molecule which lacks the following elements of symmetry: plane of symmetry, center of symmetry, axis of improper rotation and axis of proper rotation, is called asymmetric molecule. The molecule which does not contain sigma I, Sn and Cn is called asymmetric molecule, which means having no symmetry. A means no, D means devoid. Thus, the dissymmetric molecule lacking axis of proper rotation also, in addition to plane of symmetry, center of symmetry and axis of improper rotation, is called asymmetric molecule. That dissymmetric molecule which lacks axis of proper rotation also, in addition to sigma I and Sn, is called asymmetric molecule. All asymmetric molecules are dissymmetric also, and both dissymmetric and asymmetric molecules are optically active. In nutshell, we can say that the molecule lacking axis of improper rotation is optically active. The molecule which does not contain axis of improper rotation is optically active because it includes sigma I and higher level of axis of improper rotation. Let us see it again. S1 means C1 into sigma H, and it is nothing but sigma. S2 means C2 into sigma H, and it is inversion operation. S3 means C3 into sigma H, and similarly higher order of improper axis of improper rotation can be written. S1 operation is nothing but reflection operation, while S2 operation is nothing but inversion operation. Thus the SN operation includes both reflection and inversion in addition to improper rotation. Thus, we can say simply that a molecule lacking axis of improper rotation is optically active. Optical activity and point group. The molecule belonging to the following point groups, which lack plane of symmetry, center of symmetry, and axis of improper rotation, may be optically active. The molecules belonging to following point groups which lack these elements of symmetry, plane of symmetry, center of symmetry, and axis of improper rotation may be not essentially optically active. For example, if a molecule belongs to CN point group, which contains E and CN and lacks sigma I and Sn, may be optically active. Let us see an example. C1, C2, C3 point groups. The molecules belonging to C1, C2 and C3 point groups which contain only axis of proper rotation and lack sigma I and Sn may be optically active. For example, bromochlorofluoromethane is optically active, which belongs to C1 point group. DN point group such as D3, the molecule belonging to DN point group contains E, Cn and n number of C2 dash perpendicular to Cn, and thus these molecules don't have sigma I and Sn, and hence the molecules belonging to DN point group are also optically active. For example, let us see D3 point group. COEN whole 3 triple plus belongs to D3 point group and it is optically active. Thus, the optical activity of a molecule can be predicted from its point group. Optical inactivity of dissymmetric amine molecules. Ethylmethylamine molecule contains only identity element of symmetry and no other element of symmetry. Its point group is C1 and it is a symmetric molecule. The molecule which does not contain any other element of symmetry than identity is called asymmetric molecule. Its point group is C1 and it is expected to be optically active, but it is not true. Despite this, it is optically inactive due to the fact that its D and L forms are in rapid and dynamic equilibrium with each other because of low energy barrier of interconversion, which is about 30 kilojoule per mole. The D and L forms, dextrorotatory and levorotatory forms of ethylmethylamine are in rapid and dynamic equilibrium with each other because the energy barrier of interconversion is only about 30 kilojoule per mole. As a result, the ethylmethylamine compound occurs as racemic mixture of D and L forms and it is optically inactive. This phenomenon of conversion of D form into L form is called configuration inversion or pyramid inversion. The configuration or pyramid inversion in chiral amines has been demonstrated diagrammatically here. It is ethylmethylamine molecule. Its D form is in rapid and dynamic equilibrium with L form. Thus, ethylmethylamine occurs as racemic mixture and it is optically inactive. Now the time for self-assessment. Answer the following questions related to H2O2 having open book structure. Write down the elements of symmetry present in H2O2. What is its point group? It is expected to be optically active or inactive, and is it optically active or inactive, and why? We have to write down the elements of symmetry in H2O2, its point group, and we have to predict its optical activity and what is the reality about its optical activity. Here is the answer. H2O2 molecule having open book structure has two elements of symmetry, identity and C2 only. Its point group is C2. It does not contain sigma I or Sn, and H2O2 is expected to be optically active. But it is not true. H2O2 is optically inactive because its D and L forms are in rapid and dynamic equilibrium with each other, just like ethylmethylamine. Now the time for another self-assessment. Answer the following questions related to ethylmethylphosphine. Write down the elements of symmetry present in it. Write down its point group. It is expected to be optically active or inactive, and we have to write down the reality about its optical activity. Here is the answer. This is ethylmethylphosphine having trigonal pyramidal shape. The elements of symmetry present in it is only identity. It has no any other element of symmetry. Its point group is C1. Ethylmethylphosphine is expected to be optically active because it does not contain sigma I or Sn. But it is not true. It is optically active. It is expected to be optically active, and in reality also it is optically active because its D and L forms are not interconvertible due to high energy barrier of interconversion. Ethylmethylamine was optically inactive belonging to C1 point group because its D and L forms are rapid and dynamic equilibrium with each other. But ethylmethylphosphine also belongs to C1 point group and it is expected to be optically active. In actual practice, it is optically active also because its D and L forms are not interconvertible due to high energy barrier of interconversion, which is greater than 100 kilojoule per mole, and therefore this ethylmethylphosphine molecule is optically active. Thank you for watching the video with concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.